Great, thanks a lot. So first I want to thank the organizers for giving me the opportunity to take part in this extremely interesting meeting. So I'm Laurent Daudet. I'm on leave from my position of professor at the Université de Paris, but I'm now CTO, full-time CTO at Lighton, which is a startup that was created 4 years ago to do optical processing for machine learning. So, of course, I should not take all the credit, and all the credit should go to my collaborators. I have 3 co-founders at Lighton: Igor Caron, who is now a CEO, and you might know him from his past life, where he was having the blog Nuit Blanche on compressive sensing. There is Sylvain, who is our expert in optics, and there is Florent, who is an Ellis Fellow, who is our advisor in machine learning. I know we have an engineering team at Lighton, about 16 people in optics, computer science, software engineering, electronics, machine learning, and so on. So yes, I was very interested when I read the goal of this meeting, which was to start from physics to build machine learning algorithms. And eventually, the ultimate goal would be to build future energy efficient hardware. Well, at Lighton, we sort of do it now. We already have some new hardware, and we use physics, well, to propose some new hardware, also as inspiration for machine learning algorithm that hopefully would feed each other. But we also go to the whole machine learning applications, which includes, as you will see, going back to physics. So we have some physical applications on it. But since we want to have full-scale hardware on real-life machine learning application, or it's not quantum, I would say not quantum yet, but you will see how it relates. I mean, it's also based on wave interference, but of course we do not have a single photon, so sort of what makes a quantum computer. So yes, just to start, what's wrong with AI? So I don't know if all of you are aware, but there was this a few weeks ago, there was this natural language processing model called the GPT-3 that was released, and it has 175 billion parameters. So to train that, well, if you have the best GPU in the market, V100 NVIDIA, that would require 355 years and $4.6 million to train if you price that at the lowest price you can find on the cloud. So of course, in terms of reproducibility, or even, I mean, who can access that? So it could be an issue, because you could say that our imagination as machine learning engineers and so on could be getting limited by compute. Okay, it's on a research side, it's also on the business side. Satya Nadella, who is CEO at Microsoft, recently said that the world is running out of computing capacity. So that's definitely an issue. Also, since then, in the last 4 years, actually, when we started Lighton, there is what we call a Cambrian explosion of specialized AI chips. So many of them are just different architectures, still based on silicon, where you have plenty of tricks to, well, still push Moore's law a bit further, multi-layer, slicing, dicing, and so on, all these new techniques. They do wonderful things, but still we have to go beyond pure silicon. And yes, one way is to go beyond pure silicon and beyond von Neumann as well. That was already discussed in some talks earlier today. The von Neumann, the bottleneck where you have to access memory, still remains and gets stronger as ever. So of course there is quantum, but there's also classical optics. And so at Lighton, we have such a classical optics coprocessor. We call it OPU for optical processing unit. So what is an OPU? So it's a coprocessor specialized in only one type of operations that leverages high parallelism of free space optics. And high parallelism, I'm going to give numbers on that, but it can be used to handle very high dimensional signals. It's the benefits are the speed, the size, as I said, also the low power consumption. And yes, many people think of free space optics as ways of doing Fourier-based, for instance, convolutions, but that's not what we are doing. It's extremely hard to compete with GPUs on their sweet spot, which is convolutions. Instead, we use a randomness of a natural phenomena, randomness in that case of light scattering through scattering material. So the main principle is extremely simple. If you have a laser beam shining some sort of a special light modulator, think of a video projector, for instance, that's the chip that turns digital data into an image. And then it goes through some scattering material. The first experiment were done literally with a layer of paint. And you capture the resulting pattern on a standard camera. So if you just see that as a system, black box with input and output, the input is you can see that as a vector. The output as well, you can see that as a vector of finite size. And since the physics is linear, there has to be a transmission matrix describing all the propagation of light between input and output. Okay, there's a slight detail here in the sense that since h is complex valued and you measure intensity, there's a nonlinearity, pointwise nonlinearity at the output. You measure the intensity, and that's the complex field, the complex light field. So to summarize, the OPU, as we have it, performs random projections, which is multiplying the input vector x by some fixed H matrix. That's IID. You can guarantee the distribution. It's a Gaussian in real and imaginary part. And then you have some element-wise nonlinearity. The benefit of it is that it's very large because it's for free. You have it scales as the number of columns scales as how many pixels you have on the light modulator. The number of rows scales as how many pixels you have on your CMOS sensor. So it's million by million. So if you, this is really the equivalent of handling 10 to the power of 12 random coefficients with the guaranteed distributions, but of course without the von Neumann bottleneck, because your physics give it for free. You have access to these coefficients. You don't have to generate them. You have access to them for free. And it's also fast because this light modulator, like in a video projector, typically it flickers at 20 kilohertz to do that. So you can do the kilohertz type of operations. So if you just multiply these three numbers, you have the equivalent of 10 to the power 15 multiply accumulates per seconds. So I have to emphasize, they are not non-von Neumann, they are not programmable. Still, they are multiply and accumulate operations. Why do we do that? Why do we need random projections? Well, they are very well matched to the statistical nature of machine learning. You can see that as an optimal mixer, equalizer, preconditioner of information. But if you know the Johnson-Linden-Strauss lemma, and everyone who has studied compressed sensing knows that this is a way to doing random projection, multiplying by random matrices. Fundamentally, you keep the information, you change the dimension of a vector, but you keep the distances and the angle. So what you can do data compression and still do your machine learning on the compressed data, or you can do embeddings in higher dimensions. You can do data expansions, dimensionality expansion. So if you do deep neural network, it can also be seen as a dense, fully connected layer. That's also used to do data compression very commonly. Of course, if you want to do it in large size on standard CPU or GPU, as I said, because there is this memory access, you have to generate random numbers, you have to access these big matrices. It's very cumbersome and it's limited in size. But now, what does it enable if you have some physical device that makes them in order 1 type of complexity with virtually no limitation in size? So we've employed this type of architecture, this type of computation, like shown here with this Flare Lighton logo, mixing the OPU with standard CPU or GPU. It's not here to replace. We are not competing with CPU or GPU. We are just boosting their performance in this type of dense matrices at very large dimensions where they are not so good. So it can be used as a preconditioning for randomized numerical linear algebra, or more precisely, randomized SVD. It can be used as to do transfer learning for deep neural network, sketching for change point detection, or yes, this reservoir computing as well, when you have a feedback loop as well. That's usually appropriate for time series. Reinforcement learning on the latest one is direct feedback alignment to train deep neural network. I'm just going to give now a few examples of what we've done using the OPU. So the first one is transfer learning, and we have examples in image or video classification. Of course, you know how you do deep neural network for image classification. It's very inefficient because it requires a huge amount of data. So transfer learning, you pre-train your network on a large amount of generic data, but you do it, you do it once. And then if you have some specific database that's somehow similar to the one you've trained on, you only adapt the final layers, and that's very fast. So here, this is the example. You start with a standard, say, VGG16, but we've done it with the ResNet and any type of architecture, really. You pre-train on ImageNet, for instance, 1 million images. You have all your coefficients pre-trained. And now comes your second data set, STL10. And what you do in transfer learning, you keep the convolutional layer unchanged, and then you only adapt the dense layers, right? So the standard approach is to do your backprop on that. But instead here, we do this random projection that we can do very fast with the OPU. And then you do a standard ridge regression on the random features that you do on a CPU, right? So it's really a hybrid pipeline. The first layer, this is really the sweet spot of the GPU. The random projections, it's handled on the OPU. And then the ridge regression done on CPU or GPU or whatever. So we have some benchmark. I'm not going to play the video, but just to give you some type of typical result when we compare with or without with just a NVIDIA GPU or with NVIDIA GPU plus Lighton's OPU. And the classification results are very similar, same test accuracy, but the training time has been divided by 8. And we make a crude estimate of the energy as well, because it's faster and the OPU consumes very little. It's also a very significant reduction of total energy that's been needed to do this whole training process. And this is, I have to emphasize, this is for the whole training process, and not just for the random projections. So end to end. Yes, so it's not, we had some collaborators, David Rousseau and a collaborator who employed that to do classification of LHC collision events. So applications in particle physics. So this I'm just giving this graphics here just as an illustration. We had absolutely no part in it, but they get a very good result combining, again, the standard techniques with the OPU that gave a boost in performance. It's going to be presented in this particle physics conference this summer. If you are interested in more like the theoretical justification on why it works, we had collaboration by Ruben Ohana, who is currently doing a PhD at Lighton on that INRIA here in Paris. And he's studied with some collaborators the type of kernels it amounts to. And we know since a long time, but especially since the very inspiring paper, Neurip's paper by Haimi and Reich about the random features to approximate large-scale kernels, that yes, random features are very good to approximate. And in our case, with our distribution of the random matrix and our type of nonlinearity, Ruben could really work explicitly the type of kernel it amounts to, and this is what's written here. Yes, so that was my first example. The second example that leverages the OPU is an algorithm of sketching to do change point detection. So the idea is you have a very high dimensional signal, for instance, monitoring a data center here, and you want to detect as soon as possible when there is a change in the distribution of the data. And so they call the algorithms NUMA, that's scalable model-free online changement detection. And the idea is very simple and extremely effective. So you have your data that's streaming, and at time t, you have a new vector in high dimension, say 10,000, 100,000. And then you do the random projection. You have what's called a sketch, and you add it to the sketch at previous time with a forgetting factor lambda. And then you update your sketch, and you repeat for the new time step. So very, very simple and very efficient if you have the way to compute efficiently the random projections, because otherwise, apart from the random projection, it's just multiplying by a constant and adding to the previous sketch. So what they do is not only compute one sketch, but compute two sketches in parallel with two different forgetting factors, one with a long forgetting factor and one with a short forgetting factor, and you compute the difference between the two sketches. So if the signal is stationary, the difference would be small. If it's larger, then there might be a change point. The nice thing is, because you have some physical guarantees on the distribution of the random matrix, you can compute some bounds, some probabilistic bounds on this difference. So you can have some probabilistic guarantees on when there is an actual change point or not. So there's a paper on arXiv on that if you want to have all the details. The type of result is that in terms of false alarm versus misdetection, you have to look at the curve in purple here. It's on par with the best method, the ScanB, which is a state of the art. But the nice thing is that you need less samples to trigger an alarm. And also, I was saying in terms of computing time, you can really see the benefit. Again, so the x-axis here is the dimension of the signal. On the y-axis is the time it takes to compute the sketches. And as I said, the OPU, the random projection, is fundamentally order 1 up to a very small pre and post-processing. The computing time is more almost independent of the dimension. Or you could even go 1 decade further to 1 million. method, which is an approximation of the random projection, are in log n type of computation. So this was used by one of our engineers in computational chemistry to do the detection of conformational changes. So this is a work by Amélie Châtelain. So in computational chemistry, well, the goal is to find metastable states when you do this big HPC computation for molecular dynamics. And of course, the big application is in drug discovery. You have all this huge computation that takes a big part actually of the computation that run on these big HPC clusters in the world. But then you have many time steps, and you want to know when there's a big change, when it's or if the computation is stuck is in some local minima of the energy. So we use the NUMA algorithm change detection to do that. And I'm not sure playing. I'm going to try to play a video if I have the right bandwidth, if I can. So if you see on the left, this is some computation that was made by D.E. Shaw on a supercomputer, and we analyze this data, and we detect when there are some changes in the conformation with our algorithms. A very light layer of unsupervised AI on top of this HPC computation. The idea is to save time overall. And we could confirm that the change point correspond to actual changes of conformation at a much lower complexity than what is usually done on this type of very large molecule. It's important to emphasize that here we are in extremely high dimension. I think it's 700,000 dimension to do that. So this is not some type of computation that can be done easily on standard computers. Another type of application that we do with the OPU still has to do with linear algebra, is to do randomized SVD, and the application is to do recommender system. So SVD, when the matrix X is too large, doesn't fit in memory, a very standard way of doing is to compress it in the largest dimension by multiplying by a random matrix. So you approximate X by X hat here, and X hat, you do the SVD because now you are in small dimension. And by perturbation methods, you can get an approximation of the real SVD of the large matrix with some bounds on the error that you make. So we did not invent the algorithms. This is well known in the randomized SVD community. But what we did is to use our optical machine to do this compression, to do this multiplication arcs equals X hat here. So it's really some pre-processing in order to do the linear algebra. And okay, there were some funny examples in doing that for a recommender, a very basic recommender system, where you say, hey, I like Toy Story, and we were happy because the system answered, you should watch Toy Story 2, which, well, sort of seems to work in a sense. We are not claiming that it is state-of-the-art recommendation. It's just a sanity check that it seemed to do the right type of rank reduction that is needed for randomized SVD. And finally, my last case study is about reinforcement learning. We had an intern, Martin, doing great work in that. So this is a framework that's called the model-free episodic control. So again, this is maybe not the state of the art. It cannot learn how to play Go, not yet, but this is extremely simple. You match the current observed state against all the record of previous attempt, and you choose the action in the past that served you best. So the two components is to keep track of a reward value for each state action pair. And then you have to look for the nearest neighbor in all your memory. and check the one that for which the action was most interesting, that gave the highest reward. And of course, to do that, you need an efficient way of computing nearest neighbors, and that's where the OPU comes into play. And we did that with standard Atari games like Pac-Man, or we have also Space Invaders if you prefer, but this is just to show my age. I used to play that as a teenager. And we are using the OPU just to compute what computer scientists call hash codes, just very compressed version of the screenshot, really, that defines the state. And because of this Johnson-Lidon-Strauss lemma, they are locality preserving, in a sense that you preserve distances. If two screenshots are close, the hash codes will be close as well. So you can do fast nearest neighbors in the space of hash codes. And that's what we do with the OPU. And this is just Pac-Man played on an by this method. So it's fundamentally it's sensitive things, and it's managing to play Pac-Man. This is just a simple example, of course, but at least it shows that even this very simple method can do some learning in a sensible way. So just to mention, we have other case study. If you go on our webpage, we have plenty of interesting studies like supervised random projection, where you do random projections, but then you include also information from the labels to have more useful embeddings. And the last one, I'm not going to talk much about it, is to do direct feedback alignment, which is an alternative to backpropagation to do the neural network training. That has the big advantage of updating the layers in parallel, and also to be more plausible than backpropagation in terms of biology. So just in the last 5 minutes, I'm going to talk about more like the technology. As was said before, it's hard for a company to make hardware. So what we want is to have users before we have actual products. So what we decided was to have some prototypes available in the cloud, and it's already a reality. We have a OR 1.5 OPU that's in the cloud. They are hosted in 2 data centers here in Paris. And researchers get free compute time through the Lighton Cloud for Research program. And if you are interested, you will be fast-tracked because we already know who you are. You already have your credentials. And just as an example, we had a New York paper last year that was really user-contributed. So this could be also interesting for you. This is extremely simple to use. It's compliant with scikit-learn, Python, Jupyter Notebook. You import a library here, just import some specific functions to do pre-processing, and then send the data to the OPU, and there you are. That's it. You can do the random projection at the speed of light. Yes, just one common misconception. Free space optics is bulky. And I recently gave a talk in Silicon Valley, and I don't know who chose the illustration, but I didn't send any image for that, and someone took this picture of a big optics table here to do free space optical computing. And yes, possibly some experiments are like that. And it actually started like that in the experiment 4 years ago. It was really a lab experiment in the physics department of École Normale here in Paris. But actually, this is what we call the photonic core that we have today. And to have a scale, this is a scale. So really matchbox size, and it does exactly the same function as a fully fledged lab experiment that we had before. So as a future, we plan to integrate all these photonic cores on PCB to combine more function and so on, and to integrate with silicon photonics and so on. And I'm going to finish here. The take-home message is that, okay, optical computing has a long history, but we can really see a revival of these techniques that's very relevant in the framework of machine learning and AI, because there is a huge need of very large data, a lot of data, fast and energy consumption as well. We don't want to replace silicon chips. We want to boost them, to complement them, the standard silicon chips or the quantum as well. I can discuss that as well. So it's a non-von Neumann paradigm. We don't learn the coefficients. They are fixed and they stay fixed over time. But this is the benefit of this starting point, is that we can already do at-scale computation with off-the-shelf components. We did not invent new components. We are just a small startup. We just combine in a very different way the components that are available for video projectors, for CMOS cameras, and so on. And well, we have a single elementary operation where the complexity goes now from order of n squared to order 1. And I have shown you today a few use cases where it was useful, but well, what's your use case? And if you want to play on our cloud, you're very welcome to do it. Just log on our website, send me an email. We have plenty of examples on what you can do with it. And that's the end of my talk.
Okay, thank you very much. The floor is open for discussion. Let me see whether we have some questions. I think not yet. I had some questions myself. So the so this random projection, this is stored once, if I understand.
That's correct. Yes.
So is there any choice in that, and how random is that? And
so it's okay. There is no choice in a sense that you've got 10 to the power of 12 coefficients that are drawn once and for all, but they are guaranteed by the physical principle to be Gaussian IID. They are complex values, so they are Gaussian in real and imaginary parts.
Right. I see. But you have no choice.
You have no choice. You don't program them. You can measure them if you want. You can calibrate that by a sufficient number of input/output. Eventually, you can measure submatrices of that. But
are two devices identical, or
no? Two devices would be different.
Yeah. Okay.
Maybe
so
I have a question.
Yeah, Florian.
Okay. Yeah, about the hashes. I was always under the impression hashes are constructed in a way so that they don't collide. You put in something that may be structured data, but you get very different hashes. I thought that's the point. But now you tell me, no. If there's a next neighbor in the original data, indeed, also the hashes. Is that a particular form of hash, the one you generate, or is that actually general? I was just surprised.
Yeah, so it's you're right. I mean, there is always a trade-off in the size of the hash. We can really choose the size of the hash code so that the probability of collision is as low as possible. And there's never a zero probability. It just depends on the size of the data. So you have to play with the size of the hash code. And of course, the longer hash code, you reduce the probability of collision, but then the longer the computation for the nearest neighbor. And actually, this is a very standard technique, this locality sensitive hash code. We just have a physical implementation of that, but we did not invent that. This is a good, well-known technique for hash codes. But yes, you're right. This is all based on this distance preserving property of random projections.
Okay, let's see whether we have any other questions. So can you say something about the quantum features that you could potentially what kind of functionality, what kind of different things could you expect to be able to do with the quantum features of light?
Yes, this is also a small experiment a small project that we are starting now at Lighton. That is to do the equivalent of what we do, but with quantum sources and detectors, to have some programmable linear network, but I cannot say much at the moment. This is just take the quantum equivalent of what we do, but to do some random mixing in a programmable way. But yeah.
Thank you. Okay, so I see there is no more questions for this discussion. I would like to thank you for a very nice talk, and it's very interesting to see your contribution to the hardware and also the invitation that we can use your systems.